Hello. Welcome everyone. In today's lecture, we are going to look at a new concept, which is the concept of strain, and we'll try to find out how we can relate the strain at a particular point to the displacements at particular point. And these relationships that we derive are also what are called as strain displacement relationship. Okay. So what are the objectives of this lecture? So what we'll do is, the first thing we'll do is first find out how the different components of strain can be related to the displacements at a point. Okay, so the strain is a tensor just like the stress tensor, and it has many of the same properties that the stress tensor has. So you'll see a lot of similarities between the strain and stress concepts. Okay. The second thing that we'll do is we'll formulate the straight tensor and recognize its similarities to the stress tensor. The third thing that we'll understand is the concept of isotropic and homogeneous materials. So these are slightly different concepts, isotropicity and homogeneity, and we'll try to figure out what is what. And because this is something that you will kind of routinely use in this class for solving problems. Okay, so let's look at the generalized concept of strain. So just as we defined the stress at a point, strain is also defined at a point. Okay, so in this case, what I have done is I have essentially chosen a point P, okay, and I have defined a small element around that point P, okay, of dimensions delta x and delta y, okay, and that is what I have shown here. Okay, so that box that I have put in here essentially is a box around a point, and this point P is in a body that is being subject to deformation. So the point P is also getting deformed. So what we are trying to understand is how we can relate the displacements at this point P in the x and y directions to the strains in the x and y directions. Okay. So if you think about this particular case, so let's say this box around this point P has this dimensions, delta x and delta y, in the undeformed state. So the body is not subject to deformation and everything is in equilibrium. So at that particular instant, this is the box or the element around this point P. Okay. Now, let's say that in the next instant or after some time, the body is deformed and it has reached an equilibrium in the deformed condition. Okay. Now, at that same point where the body is deformed, this particular element that we defined around this point P, okay, has now moved to a different location, okay, here, and at the same time it has also enlarged. So the dimensions of that element that we defined around that point P has also increased. So it has both translated and also deformed. So in that case, how do we define the strain at this point P? Okay, so if you think about this particular problem, you can see that the initial length of the box, okay, or the element that we defined around this point P is delta x, okay, which is here, okay, that is delta x, and the distance or the of the element or the length of the element along the y-axis is delta y. Okay, so delta x and delta y are the initial dimensions. Okay, now the way we have, or the way you have been taught what a strain is, especially a normal strain, is that you think of it as the new length minus the old length divided by the old length. Okay, or the new dimension minus the old dimension divided by the old dimension. Okay, so in this case, if you look at this particular case, the new length is going to be different from the old length. And how do you relate the new lengths and the old lengths? The one way you can do that is that you can say that this point A, okay, has translated from its initial location to its new location A prime, okay, and the displacement of this point A is u, okay, so that is the displacement of this point A. Now, if you consider this point B, which is the other corner, then that essentially has translated from B to B prime, okay, and this displacement is u plus delta u. Now, if you want to think about how much the length has changed for this particular element, it is going to be nothing but u plus delta u, okay, that is the new location of B prime, okay, or minus the new location for A prime, divided by the initial length, which is delta x. Okay, so let me just actually go through this a little bit more, slowly, because it's an important concept. There are two things here. One is the initial length of the box, which is delta x, and the second thing that we're talking about is the displacements. So the point A has displaced by an amount u. Point B has displaced by an amount u plus delta u. Okay, so the change in length of this particular element along the x direction is u plus delta u minus u. Okay. On the other hand, if B prime or B has also translated exactly by the amount u, then the total elongation of this particular element will be 0. It will be u minus u, which will be 0. Okay. The reason that the elongation is not 0 is because the point B has translated by a larger distance compared to the point A. Okay. So the change in length is nothing but u plus delta u minus u. The initial length is delta x. Okay. So that essentially defines your strain. Now, if you take this to the limit where this delta x is very small and delta u is very small, then essentially you get epsilon x to be equal to del u over del x. Okay, and the reason that you have a partial derivative here and not a total derivative is because u depends not only on x but also y and z. So essentially u is the displacement along the x direction, and that depends on the location of the point x, y, and z. Okay, so that is how you get this relationship for epsilon x, which is del u over del x. Okay, and similarly, you can see that the strain in the y direction, or the normal strain in the y direction, is del v over del y, where v is the displacement along the y direction. Okay, so again, the strain is related to the gradient of the displacement. Okay, del u over del x. Epsilon y is del v over del y. Okay, so again, I should probably note here, v is the displacement in the y direction. Okay. Okay. So this essentially defines the normal strain at this point P. Okay, and again we are considering only the two-dimensional case here, just for simplicity. So if you look at this point P, if the body is subjected to deformation, then the normal strain in the x direction at point P is del u over del x, where u is the displacement at point P. Okay, similarly, the normal strain in the y direction is del v over del y, where v is the displacement in the y direction. Okay. Now, this is how you define the two normal strain components. How do you define the shear strain components? Okay. The shear strain components is going to be a little bit different. So for that, what we generally do is we assume that u, v, and w are the displacement fields in the body. So essentially, at every location x, y, and z inside the body, you can look at what the displacement is in the x direction, y direction, and z direction. So u is a function of x, y, and z, v is a function of x, y, and z, and w is also a function of x, y, and z, where w is the displacement in the z direction. Okay. So if you look at this general case, then your epsilon x, okay, is going to be del u over del x, epsilon y is going to be del v over del y, and epsilon z is going to be del w over del z. Okay, again, all these are partial derivatives. Okay, and the u, v, and w are essentially the displacements along the x, y, and z directions. Okay, and they are all functions of the location x, y, and z of any point. Okay, so that is the general definition of the normal strains. Okay, for shear strains, we have to consider a slightly different case. So suppose you have this again, the same element. Let's call this point P, and then you have defined an element around that particular point P, and then let's say in this case we are only applying shear stresses. Okay, so we are going to only have shear deformation, not normal strains. Okay, so if you think of this axis as the x and u axis, where u is the displacement, and the perpendicular axis as the y axis, which is also the displacement along the v axis, along the y direction, then if you plot how this element deforms as you apply this shear stress tau xy is that, so initially it has shape like that, and when you apply the shear strains, what essentially happens is that it essentially deforms into that shape. Okay, that is the effect of shear. Okay, now the shear strain is not related to the changes in length, but rather changes in angles. Okay, so now if you think about this particular case, initially the angle between these two lines was 90 degrees. Okay, but now once you apply the shear stress, it is no longer 90 degrees. Okay, and this change in the angle is what is related to the shear strain. Okay, so now if you think about the same idea on how do you actually find out this angles, if you look at phi1, which is this angle here, that is nothing but del u over del y. Okay, remember epsilon x is del u over del x. Here we have the cross derivative. So it's del u, where u is the displacement along the x direction, and the derivative with respect to the y direction. So it's del u over del y. And this particular angle here, again just from geometry, is nothing but del v over del x. Okay? So the angle change is actually equal to phi1 plus phi2. Okay, so initially it was 90 degree. Now the new angle is going to be 90 degree minus phi1 minus phi2. Okay? But of course here I have exaggerated the amount of deformation, or exaggerated the angles. Okay, these angles usually phi1 and phi2 are actually very, very small. So in that case, you can actually use the small angle approximation, whereby tan phi is phi. Okay, so actually if you think about the expression that I have written here, this del u by del y is actually the tangent of phi1, not phi1 directly. Okay, but because these angles are small, you can make the approximation that tan phi is equal to phi, and therefore del u by del y is phi1. Okay, so that's something that you must keep in mind. Okay, now the shear strain gamma xy is essentially the sum of these two angles phi1 and phi2. Okay, so gamma xy is del u over del y plus del v over del x. I want to kind of make a note here. This particular symbol is gamma. Okay, that is not r, it is not nu, which we'll see later, it is actually gamma. Okay, gamma is shear strain. Okay, so gamma xy is del u over del y plus del v over del x. Okay, again you're looking at only the 2D case in the xy plane, and that is why you have these two. Okay, now because of the fact that the shear strains also have this complementary property, gamma xy is same as gamma yx. Okay, so gamma yx and gamma xy are the same. So essentially if you flip the subscripts, they remain the same. Okay, so this is very similar to the fact that tau xy is equal to tau yx. So you can already start to see the similarities between the stresses and strains. So this gamma is a shear strain, and this is a shear strain in the xy plane, and that is equal to gamma yx, and that is given by del u over del y plus del v over del x. Similarly, you can also write down expressions for gamma xz and gamma yz, and that is what I have done here. So this is gamma xz and that is gamma yz. So gamma xz is going to be del u over del z, and the second term is going to be del w over del x. For gamma yz, it is going to be del v over del z plus del w over del y. Okay, so if you look at this set of equations here, okay, and here, okay, the equations A and B put together, there are 6 equations. Those are what are called as the strain displacement relationships. Okay, so there are 3 independent variables, u, v, and w, which are the displacements at any point, and they can be related to the strain at that point using these relationships given in A and B. Okay, okay, so if you look at these set of equations A and B, one thing is kind of odd, because you have these 6 components of strain, epsilon x, epsilon y, epsilon z, gamma xy, gamma xz, and gamma yz. But you have only 3 independent variables, u, v, and w, which are essentially the displacement at a point. Okay, so this automatically tells you that this set of equations alone can't uniquely determine or uniquely define as strain field. Okay, because if you have this kind of a relationship, you can basically have multiple strain fields for the same displacement field. So somehow you have to constrain this displacement, the strains at a particular point, or the strain components at a particular point. And this is usually done by what is called as strain compatibility equations. Okay, so again, this is an advanced concept that we will not be covering in this class, but it is good to know that there are an additional set of equations. Well, actually, three additional equations, what are called as the strain compatibility equations. You have to use those three equations in concert with these equations A and B to uniquely define the strain field at a particular point. Okay, but for the purpose of this class, usually if you're asked to find out the strains, you'll be given the displacement field, and you'll essentially have to use these equations A and B to actually find out what the strains are. Okay, that is what we'll be doing in this particular class. Okay, so that's pretty much about the generalized concept of strain. Now we can look at the specifics of the strain tensor. Okay, so there are some small differences in the strain tensor and the stress tensor. We'll look at them in a moment. Okay, the way we define the stress tensor though, or the strain tensor though, is actually very similar to the stress tensor. So essentially, you have the normal strains along the diagonal, okay, and the shear strains are along the off diagonal. Okay, but one thing that you would have probably already noticed is that I was referring to gamma as the shear strain. Now I have epsilons. Okay, but there is a relationship between this epsilon xy and gamma xy. So the relationship is essentially that your epsilon xy that I have written here is essentially half of gamma xy. It's essentially just gamma xy divided by 2. And the reason that we define the strain tensor in this particular manner, so instead of using gamma xy, gamma xc, we use epsilon xy and epsilon xc and epsilon yz, is because if you define the strain tensor in this particular manner, then all the stress transformation equations that you derived can actually be directly used for strain transformations also. So essentially, you just replace sigma x by epsilon x, sigma y by epsilon y, and sigma z by epsilon z, and tau xy by epsilon xy, and so on. You essentially then you can use the exact same equations that we derived for the stress transformation case for the strain transformation. So that is the reason why we define this strain tensor in this particular manner. Okay, so epsilon xy is not a new quantity; it is just gamma xy divided by 2. Similarly, epsilon xz is nothing but gamma xz divided by 2, and epsilon yz is nothing but gamma yz divided by 2, where we already know what this gamma xy, gamma xz, and gamma yz are. Okay, those are related to the displacements. Okay. And the other thing that is good with defining this strain tensor in this particular manner is that you can use the same equations that you derived for, or actually more precisely, the equations that are analogous to the equations that you derived for principal stresses. You can use that to find the principal strains. The same approach you can use for finding the principal directions of strain, and so on. Okay, so essentially, whatever you learned for stress tensors can be directly applied to strain tensors if we define strain tensor in this particular manner. Okay? So, and we'll look at one specific example of where you can use the strain transformations to do something useful in the next lecture. Okay? So now I want to kind of go to a slightly different topic. It's just an aside, is that in this class, we will often assume that materials are both isotropic and homogeneous. Okay? These are kind of sometimes slightly confusing notions. Okay? So what does isotropic mean? Isotropic means the properties are same in all directions. Okay? And homogeneous means properties are same at all locations. Okay? Sometimes it looks like they are the same, but they are not. So the way you can kind of think about it is that, say, suppose you have a body. Okay? And I choose one location here. Okay? And I take out a small piece of material out of that location. Okay? And then I take this small piece here. Okay? And then I measure the Young's modulus, for example, in the x direction. So let's say this is the x direction. Okay. So I'll get one value of x Young's modulus, which is going to be the sigma that I apply divided by the strain in the x direction. Okay. Now I take the exact same material. Okay, and let me call that Ex. Okay, Young's modulus in the x direction. Now I take the exact same piece, but now I load it in the orthogonal direction, which is the y direction. Okay, I apply the same sigma. Okay, and now I will measure some strain in the y direction, and using that I can define what the Young's modulus in the y direction is. Okay, this will be like Ex will be equal to sigma divided by epsilon x, and Ey will be sigma divided by whatever strain I get in the y direction, which is epsilon y. Okay, isotropic means if this material is isotropic, means your Ex will be equal to Ey. Okay, so the property in the x direction, which is the Young's modulus in the x direction, is same as the Young's modulus in the y direction. So that means this material is isotropic. Okay, so I can do it for the x direction, y direction, z direction, or some arbitrary direction. Whichever direction I measure the property, the Young's modulus, it will have the same value. Okay, now that is the concept of isotropicity. Now, homogeneity is different. So I take this location A. Now I go to another location B. Okay, and then let me call this A. And I go to that location. Okay, this is location B, and I do the same experiment. I apply sigma. Okay, and I get an Ex. Okay, now if the Ex at B is equal to Ex at A, then this material is homogeneous. So wherever you measure the property has the same value. So here we are talking about the Young's modulus in the x direction. So whether you do it at point A or point B, the value that you get is the same. So this material is homogeneous. Okay. Now, it is possible that a material is homogeneous but not isotropic. Okay, so the way you can think of it is that, so if I now measured this the Ex and Ey at this point A, but Ex is not equal to Ey, then the material is not isotropic. But the material can be still homogeneous, because if I do the measurement at this location B, I will have Ex B equal to Exa and Eyb equal to Eya. So the properties in the x and y direction could be different, but irrespective of the location where you're measuring that property, the property in a particular direction is the same. Okay? Now you can also think of the opposite case where a material is isotropic, but it is not homogeneous. Okay, so if you look at point A, your epsilon Ex, the Young's modulus in the x direction, is equal to Ey. Okay, but now if you measure the Ex at point B, it will be different from the Ex at point A. Okay, so this is a very kind of minute difference, but something that is very important. Okay, so homogeneous doesn't mean isotropic. Isotropic doesn't mean homogeneous. Isotropic means it is related to directions. Properties in all directions are the same. Homogeneous means properties at all locations are the same. Okay, but in this class though, we will assume that every material that we are looking at is both isotropic and homogeneous. So we don't have to look at variations in properties across locations. We don't have to worry about variations in properties in different directions. Okay. And the reason that I'm kind of emphasizing this a little bit is because if a material is not isotropic, then the principal directions of stress and the principal directions of strain need not be the same. On the other hand, if a material is isotropic, then the principal planes of stress are going to be the principal planes of strain. So whichever direction you have the maximum normal stress will also have the maximum normal strain. Okay? So if a material is isotropic, then we have the stress and strain directions, the principal stress directions and the principal strain directions to be the same. If not, they need not be the same. Okay? So again, we only talk about isotropic condition because strain is always defined at a point. Okay, stress and strain are always defined at a point. So it doesn't make sense to compare stresses and strain across two different locations because in general they will be different. Okay, but if a material is isotropic, at least you know that at a particular point, the directions in which you have the principal stresses will also be the directions where you have the principal strains. Okay, so those will be the locations or the directions in which the normal strains will be maximum. Okay, so essentially you can have a one-to-one correlation between the principal stresses and the principal strains if the material is isotropic. Okay, that's all I wanted to cover for this class. I'll see you in next lecture. Thank you.